So our speaker today is Dr. Jeanine West from Flowers, Canada, Ontario. She'll speak about her greenhouse dehumidification project. And as I mentioned, Marco Dilganardis from Freeman Herbs, which was one of the greenhouses that participated in the project. He will be sharing his perspective on the technology and the project. Dr. Jeanine West is the environmental specialist with Flowers, Canada, Ontario. Jeanine's background is in freshwater biology and plant pathology. Her main goal at FCO is to identify and evaluate potential opportunities for farms to operate more sustainably. Thanks for joining us, Jeanine.
Thank you very much for inviting us to chat about the results of the project. So I guess I'll start sharing and see if I can get this to work here. Ta-da, it works for me. Does that look okay? And can you hear me okay? Those are my two key questions, Sadi.
Yeah, it looks great and we can hear you. Perfect.
Okay, excellent. All right, so I'll get started then. So greenhouse dehumidification is our topic today, and looking at whether this is a tool that we can use for dealing with the carbon crisis and our targets in Ontario and within Canada. So I just want to note that, frankly, I don't know a lot about mechanical engineering and all the calculations and math that goes behind determining effectiveness of systems for energy control and so on. We hired Dr. Jingjing Han, our key researcher for the project, who is a mechanical engineer and has over 10 years experience working on the engineering behind energy management in controlled environment agriculture. So we also have Dr. Ann Huber on the project from Soil Resource Group in Guelph. She is the environmental microbiologist and assisted with kind of similar to what I did, where we're understanding what the grower needs and trying to figure out all the mechanical engineering and how to put those two things together so that they make sense for growers. And of course, Anne has her specialty in looking at the air quality and so on and microbial populations. All right, let's see. There we go. So first of all, we start out with a humidity problem. We have greenhouses in Ontario are heated. We primarily use natural gas. You get in the wintertime, transpirations occurring, you have humidity build up inside. So this excess humidity can be a problem, can cause disease issues and add disease pressure. So we vent the greenhouse to let that extra humidity out, and bringing in that cold, dry air corrects that humidity issue in the greenhouse. But at the same time, we have a loss of that valuable heat. So if we're looking at managing our carbon footprint, and our sector is truly supportive of working towards solutions that can mitigate our natural gas consumption, how do we do this? We can't just keep the greenhouse closed and prevent that heat. So this is where dehumidification systems can be a potential solution. So we actually had two projects approved, and since 2017, initially the Greenhouse Renewable Energy Technologies project, where we purchased equipment, installed that equipment, the dehumidification units, and monitoring equipment, and started some preliminary data collection. And the subsequent project, the Greenhouse Competitiveness Innovation Initiative, allowed us to continue our monitoring and evaluation of the systems, and also look at more air quality and leaf wetness condensation issues. So for both projects, essentially we had two main hypotheses: that energy savings could be realized by using a dehumidification system. So even though it's being used to manage humidity, we did believe that it would have a resulting energy savings and ultimately a fossil fuel decrease. And secondly, that using a dehumidification system can decrease disease pressure. We looked at 4 different technologies, and I'm going to use these 4 acronyms throughout the presentation. So you might want to make a quick note of them as I'm talking here. Just keep them in mind. LDD is the liquid desiccant dehumidification system. MRD is the mechanical refrigeration dehumidification, so more conventional or traditional dehumidifier. HRV is the heat recovery ventilator air exchange system. And the prototype system that we included, it's not commercially available. We termed an ERV. It's basically a combination of the heat recovery ventilator, the air exchange system, and the liquid desiccant system. And in each situation, at each greenhouse, we had these installed in different zones. We monitored the energy and heat consumption. We monitored the relative humidity. We also tracked other things with their computer control systems, like when their vents were opened, indoor and outdoor temperatures, things like that. And we also performed air quality testing, both in the greenhouse at the crop level and in and out of the different units. Using 2 different methods, we used 3M petrofilms for yeast and mold, which is something that Anne's group has developed. And we also did some analysis on air quality that we sent out using more traditional methods. And in the last project, we did some more leaf wetness and condensation work. So I'll just review each farm and briefly and what technologies we had installed. So at the floriculture greenhouse, they had the same crop in each of the 3 zones that we had installed in equipment. It's slightly different stage, but it was the same crop for the whole greenhouse. So they had a liquid desiccant system, the LDD system installed. Eventually that zone became more propagative and the humidity levels were increased. But there was also another zone with heat recovery, the picture in the middle, and on the far right, the mechanical refrigeration dehumidification, the MRD system, was installed in another zone. So these zones were slightly different sizes and had some different factors. Exterior wall for the HRV, for example, but Jing is a brainiac and was able to make some adjustments in the numbers and adjust for those variations. At the herb greenhouse, initially they had both liquid desiccant and mechanical refrigeration units installed. They moved greenhouses, so they reinstalled them at the new greenhouse location, then eventually removed the MRDs and only had the LDD units. They had 2 in each zone and then a control zone. So they had a total of 4 units with 2 zones, but there were crop differences. So effectively, the data that we got from there was mainly from this site was mainly from the LDD from 1 zone. Excuse me. And at the vegetable greenhouse, again, here's an image of the prototype. It was a humongous unit. It was very challenging to install. I imagine in the long term, these units will shrink and get easier to install. This was quite a production, actually. But this, again, is the combination of liquid desiccant and heat recovery or heat exchange. So when I get into the results, I want to preface it with a mention of some of our challenges that we had that affected our data. These are the main ones. There were lots of issues that happened, but these are some of the key ones. In some cases, the units, particularly LDD and MRD systems, were undersized. So the performance may not have been optimal. So we want to be careful how we present the data to not diminish what these systems are capable of. The herb greenhouse moved, as I mentioned. Then there were some maintenance issues. These units needed new towers because they were getting older. That affected the data collection, mainly not because of that. That should have been a quick fix, but supply chain issues and COVID obviously had some impacts on getting technicians and getting materials shipped from overseas. So that delayed some of the work that needed to be done. And similarly, there were some maintenance issues at the flower greenhouse that affected the data for 2022. And the vegetable greenhouse had quite a few issues that affected our ability to collect data. They had a crop change. They moved from tomatoes to peppers, and essentially there was no data for the second portion of the project. We did complete on-off trials whenever possible, particularly in places where we never really had great control zones. It's difficult when you're doing things at a larger scale in commercial greenhouses to have true control zones that are identical. So having an on-off trial where you have a week where the unit is off and then a contiguous week immediately afterwards where the unit is on, at least 2 weeks usually, I think we did, so that we could look at similar conditions in the same zone. So we did select data from what we had available to present today. And I think another note to keep in mind, the greenhouses at all times had the ultimate control. The owners and the growers had control over these systems. We didn't have complete autonomy. These are commercial crops. They used heating and ventilation to control the conditions inside, and they were able to override our system if needed. So there are times when our systems weren't run as we would have expected them to if it was a complete lab experiment. Excuse me. So I'll start out with, I'll talk about each of the technologies in turn. And I'll start with the liquid desiccant. Essentially, this is a brine regeneration. So hot water energy is used to regenerate the brine. So the air flows across the brine, and the brine is able to remove that humidity. After a while, the brine is saturated and it needs regeneration. And then it can continue taking humidity out of the air that's going by. So it's kind of a pretty cool concept. And it does work for most of the year. I've got a summary here of effective except in summer. Essentially, in the summer, there's no advantage to using the unit, and you'll see that as we go through some of the slides. But venting happens all the time in the summer to manage temperature. Outside temperature is not cold, you're not heating, you're not using natural gas in those cases. So it's less relevant in that situation. All right, so here I'm going to get into some data. And I'm not sure what colors exactly your table will show up as, so bear with me. I'm going to walk you through this table. This is monthly energy consumption that's averaged. And really, we're comparing the treatment technology with traditional ventilation. So I'd like you to look first at the greeny blue maybe column that you see on my screen. It's green. This is when we're using the LDD. So the total kilowatt hours in a month averaged out when this unit is running. And then the columns to the right are when the unit is not running and traditional ventilation is used to manage humidity. So initially, I'd like to just compare the first column here in this blue-green to this sort of pinky yellow first column of ventilation. And if we look at January alone, we can see that it's about 250,000 kilowatt hours in the month of January to run the unit. And by doing traditional ventilation, the calculation showed us that we use about 235,000. So actually, you use less energy venting. Oh, well, that's not quite what we were expecting. So we know from other research, particularly research on roses, that when a greenhouse is vented at night, for example, the vent opens, the heat and the humidity comes out, and you close the vent. And now there's been a temperature drop, a significant temperature drop inside the greenhouse. Heat starts getting pushed into the greenhouse. You have a big influx of heat there to replace that lost heat, which is what we're trying to prevent with this dehumidification project. But that influx of heat is important because it actually can, it's proposed by other researchers that influx of heat generates a big transpiration push by the plants. So even at night, all of a sudden now you have this huge amount of humidity getting pumped into, pushed into the greenhouse area. So you have to manage more humidity than what you would have had to if you hadn't changed the temperature in the greenhouse and done the venting. That research study that we referred to, it claimed up to a 57% increase in heat loss. But this is huge. And we thought, well, I don't know that that's what we're seeing, and it could vary depending on our crop, crop stage, type of crops, transpiration rates, irrigation rates. So we said, okay, what's reasonable? Let's take the 0%, but let's not do 50, let's do 20 and 40%. And we'll get a sense of if this is true, that this happens across the board with different plants, what's the average heat loss, and what would the new equivalent of energy required to heat the greenhouse if that extra transpiration happens. So when we compare the first column, this 250,000 of kilowatt hours, to additional heat loss because of that transpiration, we're looking at 260,000 and 430,000 kilowatt hours needed. And if we were to go to 57%, the way the paper suggested, that would even be higher. So the energy required to maintain the greenhouse temperature and humidity in these cases is definitely higher than relying on the dehumidification system with the LDD. And similar results are evident throughout the other months, with less apparent effect, obviously, in the summer months. So these zones, as I mentioned, are not always exactly the same. So we compared them, we standardized at Jing, I should say, did the math to standardize these to equivalent square footages. So we have the a cost per meter squared per month here, using 2019 rates for natural gas and electricity, and 2021 rates, because they are different. There's not a huge difference in the price per gigajoule, 6 to 7.7 between the 2 years, but electricity was hugely different, so almost double in 2019 compared to 2021. So it does have an effect, particularly if you're dependent on electricity or natural gas, depending on which one is switching prices. So we did this analysis, and again, I'm using similar, basing it on no extra transpiration, using this LDD dehumidification system. It is slightly better at the cost per month, the average cost per month through the winter months, compared to using ventilation. So even though the other graph indicated that maybe it was a little bit more, that was not comparing over the same square footages. And when we look at the other months, the shoulder months, typically March, April, November, December, and we look at different rates, it's fairly similar. The cost, it's not saving us a lot of natural gas and energy savings. But that's not the only thing we're looking at, right? We're also looking at, is it managing humidity? So let's have a look at that. If it lets me change my slide. There we go. So this is a bit of a complicated figure to start out with, but you'll kind of get the flow of it if we walk through it here. Essentially, the end of the story is that the liquid desiccant system was effective at maintaining RH better than venting. So having that in your head, let's have a look at this slide. So we've got this blue line along the top, which is our percent relative humidity. And then each of these bars is showing us the amount of time, the percentage of time when the unit is running that the RH is over the set point. So we know that the system did a good job of managing, this is when the system's on, it was over the set point of 80% quite a bit of the time. You can see these sort of dashed bars, lightly hatched bars here. 90% of the time, it was over the 80% set point. But when we get to over 85%, it's quite a bit lower. So on average, about half the time, particularly through the winter months and shoulder months in the spring. In the summer, it was not as effective, and in late fall, early winter. But through these winter months, definitely, very rarely over 50, 60%, past 85%, and almost never over 90%. Whereas in the summer, it's not able to manage that. So that's where our initial comment was LDD is really important, and it's effective in most months, winter particularly, and in shoulder months, but not so much in the summer. But definitely there's a really strong control here by using the unit to manage RH. All right, so looking at another technology, the mechanical refrigeration, dehumidification. Again, it generates a small amount of heat. It runs primarily on electricity, but it runs on electricity, I should say, but of course the greenhouse is still depending on natural gas for overall heating. We're going to show you data from the flower greenhouse since we have more data from that. And we do have some on-off trials here that we can share with you. So this is a similar table to what I showed you for the LDD. So for MRD, the mechanical, like conventional dehumidification, we have some slight, oh, it does that. Sorry, it's really sensitive, my screen. This is actually a lot more exciting in a way. If we, again, we're looking at the greeny blue column here is when the unit is on. And these three columns are when ventilation is used, again, at the 0, 20, and 40% extra transpiration, therefore extra heat loss situations. So even in January, this is 2021, we were able to see the average monthly data was maybe 30% improvement in the energy consumption by using MRD versus traditional ventilation. And that situation just gets better if those plants are transpiring more and putting more energy requirement load in that zone. So that's pretty cool. And we have slightly different data for 2022. It's a little less, it's about 11% in January heat loss reduction. And but consistently over most months except for the summer, you're getting well over 10% and brokering 20% in many cases in terms of overall energy consumption mitigation. So then, of course, what's our next question? Let's make sure we're comparing different energy rates and costs of electricity versus year over year. And also, let's also look at winter and shoulder rates here, comparing 2019, 2021, and remembering that this system depends on electricity. So it, in fact, consistently shows in the winter here a better energy cost. So a lower energy cost when you're using the system versus venting for both years. And the shoulder seasons, not great, but not bad either. It's still a little bit lower. So it does help with the return on investment if energy rates are low, but you can see that there are changes depending on natural gas and overall heating and electricity costs. And these are, of course, averaged over more square meters, so they're a little more standardized. So what did it do for relative humidity? Similar graph here, except that we've added another factor. We've got on and off trials that we can share with you. So in January, if we just look at this first two sets of bars, we've got the unit on, the mechanical refrigeration unit on, and we have it off. So then we're looking at the difference here. How does this dashed bar, where it's over the set point of 85% versus over 90%, how much the time did that humidity exceed 85%? How much of the time did it exceed 90%? So really good control here when the unit's on. And when you look at the second set of bars, not as good, right? 20% more of the time it was over 85%. Almost 12% of the time it was over 90%. And again, most months are similar as we go across this graph until we hit May. May is a little different. In May, we actually had higher relative humidity in May when the unit was on than off. And that was the only month that that happened. All the other ones made sense that the dehumidification system controlled the humidity better. So what happened in May? A couple of things, but mainly the biggest reason is that the temperature, the outside temperature was about 5 degrees higher when we were running the unit than when it wasn't. So the temperature difference between the two periods when we had the unit on and off was enough that we think it really influenced the results. And if you have higher humidity outside and higher humidity inside and lots of growth and lots of temperature, then these systems just don't function as well. And then the system, of course, you're going to use venting and other reasons to manage temperature and so on inside the greenhouse. You're not focused just on relative humidity anymore. So that's why we think the May results are different, and it does support our general consideration that these units, both the LDD and the MRD units, are more effective in all but the summer months. Okay, and I'll just quickly talk about the HRV heat, the air-to-air heat exchanger or heat recovery ventilator. These, again, they use solely electricity, but the greenhouse is using natural gas to heat. You're bringing in that dry, cool air, and you're sending out hot, humid air. So they're flowing past each other, and that evens out both the humidity and the temperature. So in cold conditions, in extremely cold conditions, you're bringing air in that's so much colder than what's in your greenhouse that it's actually can harm the plants. So we had to lower the airflow rates to a very low level, and we don't think that the unit runs very effectively at that flow rate. In the summer, it's almost the opposite. You've got so much humidity outside. You've got heat outside. Yes, you've got a lot of heat inside the greenhouse, and so you're better just to vent. Like, it's not going to be effective enough to have a flow rate. It's going to be extremely high flow rate to kind of manage that, but you're also bringing in humidity at the same time. So it doesn't make sense to use in extremely hot, humid, or very cold situation. So it has to be more moderate, and perhaps our climate is not ideal for this system in the greenhouse application. So the heat loss reduction reflects this. If you look through the months, there's a bit of an improvement and an advantage in January. February was extremely cold, and we couldn't use it that much because the temperatures were too cold. April, there was a bit of an advantage, and again in November. The key here, it's not consistent in this particular climate. And did it do a good job of managing relative humidity? Again, not great. Here's a similar figure where we've got a set point of 85%. You can see the percentage of time for on and off trials. And what we saw with the MRD was the opposite for the most part, that when the unit was on, the amount of time that the relative humidity exceeded the set point was lower. And here, sometimes it's the opposite. So we have actually, when the unit was off and venting was used, it was a better situation. So not ideal. I think only April was the only month where we had a slight improvement by actually having the unit on. There's note that this was also a less humid zone. It was a more mature crop, had an exterior wall additional to the other zones, so that may have had some influences. And overall, I think the answer for this one was it has some value, but not in our climate the way the other two systems did. And finally, I would like to just talk about the ERV system for a moment. This again is a prototype system combining that liquid desiccation and brine situation and the air heat exchange concepts together. And due to the situation that we had at the farm with their crop change, they moved from tomatoes to peppers. They didn't have a lot of humidity. There were some challenges with the crop. We didn't have to run the unit as often, and so we have less data to show you, unfortunately, for this system. And that's heartbreaking for Nortec Air Solutions. They invested a huge amount in this project, and I hope that we'll have a further opportunity to explore this technology, because I really think that there's a lot of potential here. I think for this graph, we just wanted to give you an example of a few days of it running a couple years back, where it ran at night. That's the red line that's running down here, and you can see it turns on during the night and it's off during the day, on at night. So there's 3 nights here shown when it's been running. And if we look at this purple line, this is the condensation. So this is one of the leaf wetness sensor trials that Jeanine performed. And you can see when this unit is on, it really does a great job at managing that condensation. So it's obviously working really hard to bring this humidity down. So 3 for these 2 nights in a row. And then there wasn't a lot in this 3rd night, so not a lot to manage. So quite an impact there on condensation levels, and I think there's a lot of potential for this equipment. Relative humidity, this is a similar graph, not as clean as the other ones to look at, and this is when the tomatoes were actually in the greenhouse. I think if you focus on just the black bars, this is managing relative humidity, what percentage of time was it over the set point again, and look at the dark bars where it's over 80%, 85%. And you can see there's on and off, so there's a control and then the ERV. So the control zone and the ERV again. So each time, typically, the control zone has a bigger bar than the one to the right. So you can see that for most months, for March, April, May, June, July, August, September, and then in October, there's some interesting things happening, but we actually do know that in the fall of 2021, there were some calibration issues that we had to deal with. So generally, there's more control of the humidity when the ERV is in use. And it's hard to compare a lot of our data because there were some disease impacts and some differences in the crop development in both of the zones. So I think even with that, these results really show that there's some good control here. And that's usually mainly focusing on the wet mode, which is the liquid desiccant portion of this equipment. So that wraps up my discussion of the 4 different technologies. This is a reminder slide. I've kind of put everything back. These are 2 slides that I've already shown you that I've combined into one. This is a recap. And the top one is the MRD costing, and the second one is the LDD costing at the 2 different yearly rates and in the winter and shoulder season. It's just a reminder, when systems depend more on electricity, that like the MRD, you may have a more effect than systems that don't totally depend on electricity. But ultimately, the costs for using these at the 0% extra energy heat loss rates for ventilation, and it's better to use it's almost the same and sometimes better, I should say, to use the unit. But the key was that not only did it not cost you much more, if anything, or maybe a little less, it really did do a great job of managing the humidity. So in summary, energy savings potential, yes, our goal initially was to minimize fossil fuel consumption. We do think that it's at least 10, I think it's more like minimum 11% is what we observed. And we saw definitely up to 20% and potentially even more, and sometimes 30 or so percent improvement. If you go to those extra transpiration rates where you have additional heat loss, it goes much higher than that. And some of the farms have noted, up to 40% energy decreased natural gas required for heating. So that's important. The relatively cost of energy does also dictate the cost effectiveness of the system. And really important to note that the technologies need to be integrated properly with the control system to achieve optimal savings. So It is a different way of growing. It's a different, it challenges how you grow and the traditional way of thinking. We typically have the bottom heat and we do things differently to manage humidity. So there are some real growing changes that need to happen and to make these systems work well. So that does take some time. And we do think it's really important to size those units appropriately. And in terms of RH control, we felt that these units were very successful for controlling relative humidity. And it's really important when your crop is very sensitive to disease or you have crops with high transpiration rates. In terms of microbial air quality, I just want to quickly show you what we did. Again, the goal is to decrease the disease pressure. Here's Jing doing the lab sampling, so that these filters had air brought through them at a certain rate, and then the samples were sent out. And we did our own in-house petrofilm testing. So these are like a little agar sheet that were exposed for a certain amount of time. And that was pretty neat because we were able to show you, for example, that this is a sample from LDDs, a liquid desiccant crop level analysis versus when it was running and when it was not. You can see these are colony forming units of yeast and molds, and there's very, very few compared to quite high levels when the unit is not running. So there is some impact there as well in terms of their ability to clear the air. This is an overall summary that is in the final report, so I won't go into detail on that. You can find that in the technical report that's online. So what do you need to do? Please, if you're considering these types of units, we want you to investigate several technologies. Don't limit it to one because they do have different features and it can be crop dependent, your temperature range and the type of crop you have and so on that could affect it. And please demand in-depth interviews with your suppliers. They really need to understand your greenhouse configuration, your crops, your production requirements, your control systems, the climate that you're in, your layout of your system and where your energy sources are coming from. This is critical to really expect a huge amount of investment upfront just in discussing what your situation is and what technology and what size of unit is right for you. And we do believe that there is results here, and definitely for both dehumidification and for energy savings, we do think there's value, but note that results will vary, and what you find at your greenhouse after install may not be what has been observed in our research. And the only way to truly know the actual savings is to put in monitoring equipment, which is extremely expensive. So you may just have to base your year-over-year energy consumption rates as your baseline for how these systems work on your farm. And there is a full technical report available on the Flowers Canada website on the environment page. And feel free to contact me if you have trouble finding that. And I do want to say thank you to this funders of the project and the incredible partners, including the Ontario Greenhouse Vegetable Growers, Nortec, Enbridge, and the 3 farms, which just did a phenomenal job in helping us get this data. Thank you.
Thanks very much, Jeanine. We do have some questions in the Q&A, and hopefully we can get to those after Marco, and then we'll hopefully address all of those questions together. So I'll introduce Marco next. So Marco de Leonardis, there we go, is Research and Development Manager at Freeman Herbs. Marco's been in the industry for more than 30 years, and his passionate approach to horticulture has fueled an avid interest in new technologies, as well as in biocontrol and biostimulants, which he's always excited to try out because, as he likes to put it, and I'm quoting here, I would rather ride the wave than follow the wave. Thanks for joining us, Marco. Hopefully he's still on here. You want to start your camera?
Yes, I tried to start the video, but I'm not allowed to
Okay.
because you need to. Okay,
There we go.
so hi, I am Marco De Leonardis. I'm a manager of research and development at Freeman Herbs. We started using both system, the LDD as the MRD, specifically the AGAM system and the dry air system. We started with the AGAM back in 2015. We started in December 2015. And then we joined this trial with Flowers Canada in 2017. We'll be running the AGAM in the original facility for nearly 3 years, and before we moved to this new facility where we are now, and we compared both systems. So my experience, it's quite vast about these machines, and in particular the AGAM, the LDD system, so the liquid desiccant system. I find out that the liquid desiccant system, it's very delicate. It needs a very big attention in installation and in running. So when we installed it in the old facility, it worked, in my opinion, like a dream. So when it was running, we were able always to keep the humidity about 75%, which was perfect. We had it where we had basil, we had a very good control on diseases, and it really worked very well. But it's, as I said, is very temperamental. So unless you have all the settings done properly, which we did at the old facility, because we planned it while we were building the facility. So we had a heating line and a cold water line separate, that they were working like they should with mixing valves. And so we were able to control the machines properly. And we had a person in checking all daily for brine and the computer for the response of the machine. So the machine was maintained properly. That's why it worked well. And one thing that I actually had to disagree with Jeanine is that it's not true that it's not possible to use it in the summer. Is that we were not able to use it in the summer because we had not installed the dampers. So the machine has dampers that can dump the hot air outside. And if we would have installed it, we definitely would have used it in the summer, because even if it costed more, because you have use of energy to create some heat that afterward you actually expel outside of the greenhouse, it would have been perfect to control the humidity, which in the summer we cannot control. I mean, even with venting, when it's hot and with this high humidity, we have 90% of humidity outside. By venting, we're not going to reduce the humidity in the greenhouse. With the AGAM, we would have been able to, because we did reduce the humidity from 90% to 75% regularly when the mixing valve and the heating was working. So this is the point. The LDD needs a heating brine at 85 degrees. So if you don't hit the target, then the machine will not work properly. The desiccant will not regenerate, and that will be that creates the issues in the efficacy of the machine. The MRD that we use, the dry air, it's a dream for usage. You just plug it in, it works right away. However, we never were able to bring the humidity to where we wanted to. So when we moved to the new facility, we did purchase new dry air, bigger, and following the directions of the company that was selling it. And even then, we were not able to reduce the humidity to what we wanted. That's why we removed them. And that's why Jeanine thinks that we never installed the MRDs in the new facility, but we did, and they were not doing the job that they were supposed to do. And the same way, the AGAM, so the LDD, so the second machine, have never been working in the new facility. Why? because the pool facility was already built. So we were retrofitting. So we have only one line for the heating, and it's not, it didn't work properly. So it's never worked properly because we've never been able to keep the temperature constant to 85 degrees to the machines for them to work properly, because it was bleeding into the other area. So this is something that is important. If you decide to go with the desiccant, with the liquid desiccant machine, they do work very well. However, the installation needs to be done specifically for those machines for them to work properly. But if you do that, then you definitely can achieve the humidity that you need with those machines. I don't know if you have any question or any other. I don't know if my time is there, but as I said, I had very good experience with the liquid desiccant and not very good experience with the dehumidifier to achieve the humidity that we needed to. And as well, the amount of electricity and energy that we used, considering that we were able to keep the humidity to around 75, it was worth it all of it, because at the end of the day, you save so much money on fungicides, on application, everything that you need to do. And as Jeanine was saying, we proved as well that the LDD, because they have the air going through this very concentrated brine, it was actually cleaning the air from spores. And that, as Jeanine has actually, as Jeanine has proved with the Petri dishes and the research that she did in our greenhouse, there was definitely a reduction in spores where the LDD were used.
Great, thanks very much to both of our speakers today, Jeanine and Marco. It was great to hear your the results from the experiments, as well as your perspective, Marco.